Today on Xenodilodon, I present the OBIS LG, manufactured by Coherent, which is a laser that produces 355 nanometer UVA laser light. On the back, there are GB26 USB and fan connections. On this side, a lengthy warning label. And on the front, a really nice shutter to protect the aperture when not in use. This laser does require active cooling, so let's put it on a heatsink and of course, power it up. The OBIS runs on 24 volts, and it's a self-contained laser, with the laser driver and other regulating hardware and software built right in. Power is fed through the DB26 connector, which also handles interlocks and serial communication with a computer. The laser takes about a half a minute to start up, and when it does, we can take a look at how different this laser is from visible wavelengths. Don't see anything from the laser? Let's try some fog for a good beam shot. Nope, fog doesn't help at all. So how do I make this visually appealing? Here I placed a fluorescent sheet under the beam path, and the fog scatters the UVA light on the sheet, making it fluoresce. Another way is glow powder floating in the air of its container. And I have quite a lot of visually interesting things that we'll be taking a look at later. But first, let's talk about the laser hardware. The laser that I had bought as is had known stability issues. It would flicker, drop power, and rapidly warm up, even with active cooling. After connecting the OBIS to the computer, I noticed a drop in output current and voltage going to the pump diode and excessive heat buildup on the heatsink. Let's consult the manual. After consulting the manual, I decided to open up the laser. Using a thermal camera, I saw that there were two DC to DC converters that were getting rather hot. So I'm going to apply a few thermal pads on them to help them run a bit cooler. The OBIS has 4 Phillips screws holding the top cover on, and 4 Allen screws on the bottom, which hold the front shutter and the back interface onto the bottom base of the laser. After these screws are removed, the electronics inside the laser will be accessible, and there are quite a lot of things going on inside to drive the laser pump diode and the thermal management for the other optics to keep them stable. Here's the shutter assembly on the front. It's a piece of metal that slides on 2 posts. It also has a plastic backing, making it more resistant to dust. There's a little post on the front, which manually opens or closes it. Now let's take a look inside the OBIS a bit more before mounting the thermal pads. There is a large nitrogen-filled cover over the laser head itself, which is soldered onto the base circuit board. Right next to that is a board that has all the control circuitry on it, and on the front of the cover there is an optic for filtering out infrared and green. On the side of the cover is the nitrogen fill port, and behind it are 2 more boards, one with DC to DC converters on it, and the other for power and interfacing. Here is the main control board, and it contains a fairly complex looking microprocessor, along with the thermal regulation feedback circuitry and sensor interfacing components. On the top left looks to be a programming and testing interface, and on the bottom an identifier sticker. This is the board that contains those 2 DC to DC converters that were getting quite hot. There are two smoothing capacitors on one side and the interface for power regulation on the other. I'll be removing this board by sliding it off the pins so that I can apply a thermal pad on top of the DC to DC converter that is facing towards the DB26 port. If you have never heard the term DC to DC converter, I'll quickly explain what they are. They are power supplies that take DC voltage and either raise or lower it. Typically, these are called buck converters when they produce a lower DC voltage than what is supplied, and boost when they produce a higher DC voltage. Some can do both buck and boost. Both of the DC to DC boards look to be the same. They are labeled with a Traco Power sticker, and if high-end DC to DC modules are something you look for, Traco Power might have it. Now, because I don't want to risk any possible electrical problems or noise on the DB26 port, I chose to put a piece of plastic over the port, though in theory, the thermal pads are non-conductive. The thermal pads I'm using are pulled from a plasma screen TV. They will help quite a bit, and Coherent placed similar pads on other variants of the OBIS in a similar way. It may look like I am placing the pads a bit high, but I want them to also make physical contact with the metal cover of the laser's outer case. I don't think this thermal pad alone is quite thick enough, so I'm going to put an additional smaller pad on the inductor of the DC to DC converter. This process feels a lot like putting little slices of cheese on a very tiny burger. My apologies, little DC to DC converter, you just requested a single slice of thermal pad. Now the board can be carefully slid back onto the pins, and it will make excellent contact pressure against the thermal pads. I'll also be placing a second thermal pad that will go between the DC to DC converter and the sealed cover over the laser head. The whole laser can now go back together, and those thermal pads should help the DC to DC converters run much cooler during operation. Before I put the thermal pads in the laser, this was the cooling solution I used. It seemed to work well, but on occasion the entire laser would thermally run away. In addition to the thermal pads, I also decided to make a much better cooling solution to use with this and other larger lasers. For this I used a section of thick aluminum plate, two 50-watt Peltier coolers, heat sinks from a pair of Xbox 360s, and a bank of fans pulled from a Casio XJ-A 235V video projector, and it looks as cool as it is. The cooling plate can be wired up to a variety of power supplies. In this case, I am using an ATX power supply. The fans run at 12 volts, and the Peltier junctions I started on 5 volts, and then switched to 12. Between the cooling plate and the laser, I have a 1 mm thick thermal pad, which makes for an easy to reuse solution for thermal contact. I ran the tests again and I get better output stability, though the laser should not need to be this cool to get full current to the pump diode. The pump diode Peltier cooler may be failing. I can also modify the resistance on the thermistors to tune the temperatures of the optics. The thermistors look to have a common connection I labeled C, and each individual lead is S for sensor. I did manage to get the laser running mostly stable. Because of that, I won't be removing the laser head's case to take the optics apart. However, we still get to see the inside thanks to Kevin, who sent over pictures of an OBIS 355 he took apart. Under the cover is the laser head. The light is emitted from the rear and is collimated and reflected to the front. This involves the use of a few dielectric mirrors and lenses, specially made for ultraviolet applications. In this image, you'll see some infrared by the alligator clip and a green beam. Here's why that is. The pump laser diode is infrared with a wavelength of 808 nanometers at about 6 watts. This light travels through a multi-emitter fast axis correction lens, and then 2 more lenses which focus that laser light onto an optically pumped semiconductor. The OPS chip is quite complex, and there are some links in the description on how they work. Its function is very similar to a neodymium-doped yttrium aluminum garnet, or vanadium, in a DPSS laser, as the OPS chip turns 808 nanometers into 1064 nanometers. The 1064 nanometer laser light passes through a birefringent filter, which narrows the bandwidth of the laser light for a more pure 1064 nanometer spectral line. That laser light hits the output coupler, which is a dielectric mirror made to reflect 1064 nanometers and pass 532 and 355 nanometer laser light. The next 4 optics in the laser are all part of the nonlinear optics resonating cavity. Next in the optical path is the third harmonic crystal. This is made from lithium triborate. I'll talk about that more in a little bit. The light travels through at 1064 nanometers and reflects off a dielectric mirror. These are also often called Bragg reflectors. After being reflected, the 1064 nanometer laser light travels through a second harmonic crystal, which is also made of lithium triborate. It then bounces off another reflector and back through the second harmonic crystal. As the 1064 nanometer light travels back on itself in the second harmonic crystal, there is an interaction between the electromagnetic waves and the electrons in the material. This results in laser light with half the frequency. In this case, 532 nanometer light is generated. 532 nanometer light is reflected into the third harmonic crystal. In the third harmonic crystal, there is also interactions. I believe it's the generation of 177 nanometers as the third fundamental of 532 nanometers, which travels against the incoming 532 nanometer light and causes some frequency generation between the 532 nanometers and the 177 nanometers, resulting in 355 nanometers as the final output wavelength from the third harmonic crystal. Many of the optical components require thermal regulation to ensure stability since their operational tolerances are in the nanometer range. Nonlinear optics is a really complex subject. If you want to know more, there are some links below in the description for you to check out. With the technical details out of the way, it's time for more visual science. I have a piece of glass diffraction gobo glued to the front of a modified camera that can also pick up infrared, and this will let us see the spectra produced by sources of light. You can achieve similar effects with any diffraction grating film. The only real difference is that this one is glass for higher optical powers. I also have selected a plethora of items that fluoresce different colors, of which should give us a whole range of spectra to view. Each will be different when excited by 355 nanometer light. Ultraviolet lasers are often used in spectroscopy because they make just about anything fluoresce. They even make me fluoresce, and with a diffraction filter, we can see my spectrum. Strontium aluminate glow powder fluoresces quite well, as you would expect. My red glow powder, doped with europium and yttrium oxide pigments, gives off an incredibly distinct set of spectral lines from the infrared to the violet. Green glow powder fluoresces the brightest, and is quite common. This green color comes from strontium aluminate doped with europium and dysprosium. From what I can tell, both green and blue are similar in chemical structure. I think the difference is that green has 4 oxygen atoms while the blue has 7 in its chemical formula. Next are phosphors from a rear projection CRT TV. My samples are not the best, and the glass also fluoresces blue. Here's what makes red. The phosphor for red in most cases is yttrium oxysulfide doped with europium. This is the green phosphor from that same rear projection TV. Sadly, this phosphor reacted with the water in my alcohol and has degraded. The phosphor for green is most likely yttrium orthosilicate doped with terbium. And the final phosphor from that TV, blue, which doesn't seem to react with water and still works really well. The phosphor used for blue may be lanthanum gadolinium oxybromide doped with cerium and terbium. Various types of LEDs also have phosphor on them, such as this warm white. These LEDs are usually blue, with a coating of phosphors. Yttrium aluminum garnet doped with cerium and fluorine doped with manganese are commonly used, though there are several variants of phosphors used for a wide range of color. Not all LEDs are equal, and are sometimes measured for their ability to produce a very even spectrum. LEDs with a high color render index tend to be some of the best white LEDs on the market, and produce a more complete spectrum. These are often found in LED backlit TVs. LED phosphors can be formulated for a specific color band, such as on this ice blue LED. Other LED colors with phosphors can include pink, purple, green, and yellow. Most plastics also fluoresce, some with and without coloring in the materials. I honestly don't know much about what they use to color plastic. This is a neon orange plastic tool handle. Here's a yellow-orange container that glows a rather nice bright yellow color under 355 nanometers. This plastic part comes from a rear projection CRT TV. It's colored red and was part of the red CRT assembly. Some white plastics give off a vibrant blue. I'm not sure if it's the plastic itself or a whitening agent in the materials. Kapton tape also fluoresces, and while its color is normally yellow, it produces a beige light when struck with 355 nanometers. The pink lacquer on this spool of electromagnetic wire is surprisingly reactive as well, and produces quite a bit of red light. This fluorescent orange sticker might be made with an azo pigment, which could be Coumarin or xanthine based, and it's rather interesting how much broadband infrared is generated in this spectrum. Glow sticks also contain fluorescent dyes that are typically chemically excited, but can also be excited by ultraviolet. Rhodamine B is responsible for red-colored luminescence. 5,12-bisphenyl ethanol naphthazine, abbreviated commercially as BPEN, gives off a nice orange. The yellow luminescence produced by glow sticks comes from the excitation of rubrine. Green is also quite common in glow sticks for its brightness, which comes from 9,10-bisphenyl anthracene, which is abbreviated BPEA. Blue glow sticks contain 9,10-diphenylanthracene as the excited fluorescent dye. As you see, glass glow stick files are a great way to show fluorescence in a variety of chemicals. Another visually interesting thing is laser lumia. Though with 355 nanometers, it looks a bit like a retro CRT when it illuminates the zinc sulfide in this plastic sheet. Now I know that you want to see some beam shots, so I am going to use my glow powders, a speaker, and a folded sheet of plastic to make that happen. I want to thank Kevin for the pictures he sent. He runs the store, Starlight Photonics, which is where I bought my OBIS from, as well as my Ignis Red DPSS. If you're looking for industrial laser parts and surplus items, this is one of the best places to look. Trust me, I know from experience. I also want to thank all my music producing friends for the supporting music. Links for Starlight Photonics and the music tracks used are below in the description.
Oh, you're still here. Well, that is wonderful. And as much as I hope you enjoyed the video on the Coherent OBIS LG 355 nanometer laser, I would just like to let you know that it has a bigger sibling, the Coherent Genesis. And this is just the laser head. It's also 355 nanometers and uses the same OPSL technology. And in a later video, I'll be opening this up and we'll have a bit of fun with that. So you know what to do. As always, stay tuned for more.